Welcome to Brain Vision.
Estimate how many molecules of air are in each 2-liter breath you inhale that were also in the last breath that Galileo took. Hint, assume the atmosphere is about 10 kilometers high and of constant density. So we're going to work backwards from this. So the number of molecules, so n number of molecules is equal to the number of molecules in the atmosphere, so n atmos, multiplied by the probability of any molecule. So any molecule being in any two random breaths, in any two breaths. So we're assuming the two events are linearly independent. So that's simply the probability of any molecule in any two breaths is simply the probability of any molecule in any one breath squared. And the probability of any molecule in one given breath is, so we're just going to call P for shortcut. So P total is going to be the square of the probability of it being in any one breath, and we give that probability is given by V, the volume of a breath over the volume of the atmosphere, and that's squared. So we're going to calculate both of those. So V breath is equal to 2 liters. So in SI units, that's 2 times 10 to the minus 3. Volume of atmosphere, V atmos, is equal to, and so we're using standard 4/3 pi r cubed minus 4/3 pi r cubed, so 4/3 pi open brackets. So radius of the Earth is about 6371. So the radius of Earth plus 10 kilometer atmosphere is 6381 cubed minus 6371 cubed, and all times 10 to the 9. Because we're in meters cubed as opposed to kilometers cubed, because we like our standard international units. So plugging that all into P, we get that P is equal to 1.5326 times 10 to the minus 43. Now, moving on to a new page to calculate the number of moles in the atmosphere. So N atmos mass is equal to PV over KT. We're going to assume standard temperature and pressure because we haven't been told otherwise in the question, so it would make sense to do so here. So T is equal to 273 K, P is equal to 1.013 times 10 to the 5 pascals. K is Boltzmann constant, so K is equal to 1.38 times 10 to the minus 23 joules per Kelvin. And we have our volume given by this number here. Plugging that all into a calculator, we get N atmos is equal to 1.3967 times 10 to the 44, and multiplying n number of molecules in the atmosphere times the probability of any two molecules appearing in the same breath. We have the number of N, our answer, is given by 21.40 molecules, which rounded to 2, because you can't have 0.4 of a molecule, so rounded to the nearest whole molecule is equal to 21 molecules.